that? Okay. That's yeah. Over there. Oh, nice. It looked like 45 minutes. You should jump out. Well, let's take the next one. Yeah. You already got it last one. Yeah, this is the time. And communication. Yeah. Yeah. I didn't know you. It's not like frustrating. Or I don't know if this is seeming too.
Alright, let's get started. So, it's about 25. So today we'll continue to cover relational algebra, and if time permits, we will also cover part of the SQL. Hopefully, we can end the relational algebra SQL part by the end of this week. So before that, we made an announcement about the first assignment. So the first assignment, so basically the written assignments in this class are not graded. So you don't have to hand it in by the due. So if you are past due, that means we probably would already release the solution to the written assignment. If you really want to do it yourself, you can just choose not to look at the solution at that time if you are past due. Then check that against your solution later. So the written assignments, mostly the questions, the problems in the exams will be similar to those in the written assignments. So this is why you probably want to actually get familiar with the written assignments. But as I said, it's not graded. So if you don't hand it in, you don't do it at all. As long as you can do well in exam, that's fine. So about this written assignment is basically about relational algebra and SQL. So you will need to issue queries against two databases, MySQL and PostgreSQL. which are two very prominent open source databases. So we have set up the databases on our server. So I will show you how to connect to it and how to execute queries. And if you have other questions, just let me know later. So basically, the databases will be on db11.cs.utah.edu. So this computer is actually within the SOC School of Computing domain, and due to the SOC policy, they do not allow. I think their firewall blocks the database ports from outside connection. So that means if you have a computer in SOC, say your lab, you will be able to directly connect to that server, those two database servers. But if not, you'll have to use SOC computer. So that's why I know there might be some people who are not in CS department, so you may not have access to CS account. So if that's the case, we open the public account on the same server, DB11. So the username is cs6530 at db11.cs.u. You can connect that there SSH. So I'm connecting this from Windows. This is Bash on Windows. Bash on Ubuntu on Windows. If you have an older version of Windows, you probably want to use Cygwin or what's that called? MinGW, right? MinGW. So something like that, or you can use PuTTY, right? So yeah, you can connect to that, and the password is the same as the database. We put this in announcement in Canvas. So I also write it down here. So it's capital D E B as small letter CS 6530 UUSOC. These are capitalized. You can also find this in the announcements. So you can connect to this. So if you are doing your work from here, so you do not need to specify the host to the databases because it's local. But if you are connecting from somewhere else, you need to specify the host. I'll first show you the MySQL one. So it's basically MySQL-H. This specifies the host. And the username, this is a smaller case U, -U CS6530. And you need to specify -P to specify you will need a password for authentication. So then it's the same password, dbcs6530 UUSOC, and you can connect to that. So once you connect to the MySQL database, you can show databases. So as you can see, that you can only see two databases here. Basically, can you see from the back? Yeah, it's fine. So you can see the information schema. This is something about the metadata, so you don't have to worry about it. So basically, you will look at the CS6530DB. All your access is read-only, so don't worry if you issue some DML statements that modify the database. You won't happen, you will deny it, so don't worry. You can basically only do select. You can first use 6530DB, and then you will switch to this database. Then you can issue whatever query. Say you want to list the tables, just type show tables. And you can look at the schema of one of the tables using describe, say course. In the second column here. Then you will find there's three fields: course number, course name, DNAME, and type is a primary key. So here the primary key is course number and DNAME, right? Department name. Also, I think you can also type show create table course, something like that. This way you can find what are the keys. Like you can find also this is a schema, but in a SQL format. And you can find the key is actually a key dname that indicates the dname. There's an index on dname. It's not to say this is unique. It's just this is a special thing about MySQL. The key dname means it has a secondary index. We'll come back to this later in index. So that's MySQL. You can just issue standard properties here. Say select star from course, and it will print everything. So I think if you want to do something like you can write a text file, say a.sql, right? You can write some query here, say count star from course, and you save this file, and when you connect to the database, you can use this source or /dot to read this file and execute all the queries. Do this. No database. You need to first select the database. Then right? It will return the answer. So if you have multiple statements in that file, a.sql, then you will execute each of them one at a time and return all the results and print them to the screen. So you can also do output. If you don't remember the names, just type help, and it will give you a lot of commands that you can use. So what I meant was one of them is the source. The source one. This one here, execute the SQL script file. And another one that might be useful is called output something. I'll find it. Anyway, let's try it. So, no. Sorry, I don't actually remember which one. I think it's T, right? It's T. So you can type this T out.txt. Then you can do execute this. It will print the result to the screen, and it will generate a file that also contains the outputs. So if you want to save the results, that might be one useful thing. All right. So just if you use this account, remember this is a public account, so don't mess up with other people's work. If you do have to create a script file here, make sure you create a directory using mkdirs, using whatever unique IDs like your name. I don't think there's two people with the same name in this class, so that should be fine. Or you can use your UID or CSID, whatever you want. Just don't mess up with other people's script. Just remember that. So that's about it. And that's MySQL. And we also have a Postgres. Postgres, we also limited you to only use one of the database. It's an example database on Postgres document. So it's called a DVD rental. It's a DVD rental replica database. So when you want to connect to that, you first specify the host, DB11, and you can do username. This is different from MySQL. This is a capitalized U to specify the username. Still CS6530, and you don't need to specify anything for the password, but in the end, you must specify which database you are connected to. Otherwise, it will show you you don't have permission to connect to other databases. Basically, if you want to, there's a default. There's no database called CS6530, and if you want to list the database, it also won't allow you, because there's no permission for the metadata database, the Postgres. So you have to specify the database here. It's DVD rental. These are all on the written assignment, so if you don't remember this, that's fine. So the password. Yeah, and you are here in the database. So what you can do is you can also list the tables. Use \DT. That stands for describe the tables. So this will list all the tables, and you can also list the schema. \D, say actor, and you can find a lot of information about the columns types, other descriptions, and indexes on this. Alright, so that's basically about it. And you can also do standard queries, say called star or right? It will return the result. So for Postgres, if you want to see the help for the commands at the MySQL, you can type question mark here. It will also list all the commands. Remember, this is not help. Not help. Help is a little bit different. Help is for getting help for SQL statements. So it's question mark, and you will get all the commands you can use. I think for executing something is called. Let me get it as well. Select count star from a.sql. Oh, sorry. Alright, so you can use /i a.sql to execute the query from the file. And also you can issue multiple queries in the same file. You will all print all the results. It's great. And this is a little bit weird. I didn't find the equivalent of T. Don't use the T from command line because that's buffer. So the command line T basically do the same thing. It will show you like print all the inputs from the previous command. That's basically the output here. You will just print this, the same output to the screen, also record that in your file. But typically T is buffered. That means if you do that, do something like Postgres pipe T something, it will like buffer the output from the Postgres, and you will probably won't see a lot of things at the end of the printout. So that won't work. So I didn't find the equivalent of T here, so I'm not sure about that. Just I think you can still use the output thing. It's called /file o file, but this will suppress the screen output. Say I do this, and I do /i.sql. It won't print anything on the screen, but you will find your result in output, the out file. Right. So that's about it. Okay. Any questions about the database leaks? No. Yeah. So if you have any questions, just post something on the discussion or reply to them. I'll be happy to help you. And also, if you have any questions, you can also come to our office hours. Yeah. Right. So much about the database. So let's relational algebra last time and continue where we left. So basically, we talked about what's relational algebra. It's a language in a mathematical way to describe queries. And we know there are 5 basic operators where you can basically derive all the operators, useful operators from these basic 5s. And these are our example. We have rows table, reserve table, and savers table, 2 savers table. And we talk about projection, which essentially is the select part of the SQL. You throw out and everything you don't want, and only return the columns you want. And we also have selection, which is basically the web class. You can specify predicates to filter out something you don't want, and only keep those you want in terms of rows. All right, so I think that's where we left. We have left in the last lecture. So this we will talk about union and set difference. So the union and set difference is actually very intuitive. It's the same as the set in mathematics. So the union basically put all the elements in both sets together and do a distinct of that. So because this is a set, you don't have duplicate items, remember? So when you do a union, you won't end up with duplicate items, even if they appear in both sets. So set difference, what is set difference? So if you do A minus B, that's set difference. That's something like subtracting B from A, and its meaning is just return all the elements in A but not in B. So that's set difference. And something special about this, in mathematics, in sets, you don't have types, right? You can just put whatever thing you want into a set. But here, because this is a relational algebra, we restrict this set to only contain those elements with matching schemas. That means when you do a union, the schema of both sides have to be identical. And if you do a set difference, it's the same. Both sides have to have the identical schema. Otherwise, you will end up, say, uniting the both table and the reserve table. What's the meaning of that? What's the schema of the output, right? So yeah, that's about union and set difference. So we talk about for which, if any, is duplicate elimination required. Anybody can answer this? So for union, do you need duplicate elimination? Yes, right, because you can have the same element on both sides. But for set difference, do you need that? No, right, because you are basically removing elements from a distinct set. That's not, you are not going to end up with a duplicate items in that in your result. But in reality, so for union, here this is relational algebra, but in reality, in SQL, the union actually don't remove those duplicates because, as I said, in reality, due to the efficiency consideration and also the richer semantics, in reality, you use a body set abstraction instead of set. So in SQL, you don't eliminate duplicates for union. So here's an example. That's why we have two Saylor tables so that we can union them. So suppose you have these two Saylor tables S1 and S2. You can, of course, union them, right? So how many tuples are there in the end result for this? Five? Right, there will be 5 because you do the duplicate elimination. So basically for element 55, that's a duplicate in both. And for the blue one is B. So basically A minus B, or you could say A backslash B. This is the part where that's in A but not in B, this part. And B minus A is this part. And this part is exactly A intercept. So the last one is called cross product. So cross product can do operate on any two sets, even if they don't have the same schema. So what it does is basically you combine two relations in all the possible ways. That's to say you pick any elements from the left and any elements from the right and combine them into one tuple. And you do this for every possible combination. So this is also called a Cartesian product. So since the schema on left and on the right are not the same, and you are combining two relations into one, so the result schema is actually union. I would say it's not union. That's if you concatenate the schema of the second table to the first one. So, for example, let's say an example. So if you are doing Saylor cross product reserve, what you end up with, the schema is the schema from Saylor and the schema from the reserve. So you will have SID stuff, and also this will also have a SID from the reserve table. So how do you distinguish them? So basically you can put S1.SID here, and a reserve. Say we give it a shorter name, that's R. Then you put the R dot SID here, right? So in your combined schema, you will have two SIDs. One is from S1, the other is from R. So another thing you can do is you can use a renaming operator. Why is the renaming operator role? This is actually not a basic operator, but this is just for the convenience. So if you do this renaming, say you do row, what you call it C, you can use the positional notation. That's 1 to say it's S1 SID. You can do something like that, right? Something like that, and you do this S1 cross product R. That means this field will be changed to a name that is. Let's put another column. Say we put an A here. Then its name in the result schema will be A, right? This is not essential, just for the convenience. So this is the renaming part. So let's see an example. So suppose we are doing this R1. It's a reserve table and a student table. How many tuples are there in the end result? 6, right? That's 2 times 3, right? So basically, you get every combination of them. So you will have SID from R1 on the left and SID from S1 on the right. That's what you get. All right. So we're done with the basic operators. So any questions so far? No. All right. So then these are actually very difficult to use if you think about it. If you write every possible query in this way. So that's why we come up with some more useful compound operators. The first one is called intersection. So anybody have any idea how to implement intersection in terms of the basic operators? Anybody have some suggestions? Yeah.
Inner join.
Sorry?
An inner join.
Join?
Yeah.
No, we don't have join in the basic operators. You have to use the basic, right?
You can union them and then minus what's not in B and then minus what's not in A.
Right, that's right. So basically, you are doing. Sorry, I don't think I have this. So basically, what you are doing is you can do A union B, right? This is everything in both sets, and you remove something in A. Remember that Venn diagram, right? You remove things that's only in A, and you also remove things that's only in B. So you have this Venn diagram. This part is A, and this part is B. So this is A intersect B, right? This side is A minus B, and this side is B minus A. So from the union, everything, you remove this part, and you also remove this part. You end up with the intersection, right? So that's how you implement the intersection operator using the basic operators. And so for the intersection to work, you have to have the same schema on both sides, of course. Also, you can see from this implementation, because all the operators here requires the same schema for both sides. So that's also a reason why. Oh, sorry.
A minus B.
You mean, yeah, A minus B. Yes, that's a better implementation, right? Because this is basically from A, remove something that's only in A, right? Yeah, I'll just come back to this later, because these are two possible implementations in terms of the basic operators, right? But they have dramatically different efficiency, because this one presumably is less expensive, right? So that's why we have the database. We need to optimize things So this is one way to express that. This is another way. So if your database only contains the 5 basic operators, which is not likely the case in reality, but if that's the case, then you could have 2 dramatically different relational algebra or plans in your database. So the duty of the database is to choose this one instead of just that one, so that it can execute efficiently, right? Yeah. So that's a good point. This is a much more efficient one to express this intersection operator. Alright, so just as its meaning, so for this example here, the intersection is basically things that appears in both sets. Right. So the next one is the most important compound operator in database, I would say. This is something called join. A join is not something that you will see in mathematical sense, but this is useful in reality because you can connect 2 tables in a meaningful way, rather than like do a cross product. You basically have every possible combinations of your 2 tables. In join, basically you specify some condition that from a cross product, you only retain those that satisfy that particular condition. So suppose you do the result table R, join S, and we can specify some condition here, say R.SID equal to S.SID. What does this mean? This, yeah?
It means that it's going to do a select on that statement, and it will eliminate all the duplicates that don't match that.
Yeah, it's not about duplicates, but I guess it's some part of a point. Like some points, you made some point like about selecting things according to this condition, right? Well, what's that? So that's actually the semantics of this. It's about, if you think about the cross product of R, cross product S, you basically do a selection here. You require, from all the possible combinations, you only retain those that have matching SIDs, right? In this way, you can basically connect your Sailor table with all of the Sailor's information to that result table. Why this is useful? Say you want to find out, say I want to do this thing. I want to find out for each reservation. You want to find what's the rating of the sailor. I want to find out this information. So basically, I'm trying to find out for each reservation, I want to evaluate whether the sailor is capable of driving this ship, this boat, right? So that's why I want to find out what's the rating of the sailor. So suppose you do that, how do you do that? Basically, you write a join, R, join, S, and you do on SID. This is a shorthand. If it's an equality equijoin, or the condition is equality, you basically just write the common attribute here. Like basically, they have both SID in both table, and you want to do an equality join on that, then you can just write the column name here. That is the most common case, and that's why we have a shorthand for that. So this is R join S on SID. Then what next? So basically, you just want the boats. So maybe we keep the boat ID and the ratings. All right. So for each of maybe we also want to keep the SID to identify those reservations. So basically, for each reservation, unique reservation, you find out what's the rating, so that you can find out whether this sailor with SID can operate that boat. Right. This is something what's useful about John. Any questions so far?
What's the difference between join
What?
What's the difference between
Join and cross product, right? So basically, join is a combination of cross product and a selection. So it's different. So suppose, let me just put it this way. So if your reserve table have two records here, SID, EID, right? You have two records, 1, 2, and 2, 5, right? And you also have a sailor table, and you have multiple sailors, say 1, 2, right? What's the output of our cross product S? How many tuples are there?
Tables.
Yeah, what's the output of this cross product? How many tuples are there?
I don't understand.
You say tuples or tables?
Oh, sorry, I mean tuples.
Tuples.
Or I would say couples. Sorry, I would say couples. Maybe it's
Tables.
yeah. I'm sorry.
Rows
What's a tuple or a tuple?
Yeah, this word it has two pronunciation. People say tuples outside database community, but in database, some people will say tuple, some people just say tuples. It's just I mean this is confusing. Maybe sorry about that. Maybe I'll just say records. How many records are there? Is that fine? Right? So you have two records in R, two records in S. How many records are there in the cross product of R and S? 4. Right? Right. You have basically 4. You have this here. Basically, you have SID, the both ID, and SID from another table, and something else, right? You have every possible combination here. This is 1, 2, 1, something, and also another 1, 2, and this is 2 here. Every possible combination. 2, 5, 2, something, right? So if you do this, what you end up with, you can have a record that has a different SID like this one. This is SID 1, this is SID 2. And what does that mean? That doesn't mean anything, right? You are basically comparing two different sailors, and you want to say, hey, this sailor has a high rating, but the one who actually made this reservation is a different sailor. That doesn't mean anything, right? So what the join do is you add a selection here. Basically, you say this the sailor who made the reservation has to be the same as the one you join, so that you can compare, say, the rating, right? Then basically you eliminate this one here, and you eliminate this one here. So the end result will be just 2 tuples, or 2 records. Does that make sense? Yeah.
If I wanted to do a join over multiple relations, so maybe 3 tables,
Yeah.
then is there a compound operator for that as well, or do I just use that?
Yeah, actually you don't have a compound operator. You can just like use this in multiple steps. Basically, you do R join S join say a third table P. So yeah, does this one answer your questions? The difference between cross product and join? Correct.
How does it know? I'm confused how it joins with the other two. How does it know? Like in the cross product, you have every combination.
Right.
Like you said, it's like a select. How does it know which combination to choose?
Oh, it's actually so you look at all the combinations, right? You for each of them, you try to evaluate this predicate here. If this holds, then you retain this this record. If it doesn't, then you remove that.
That predicate's really hard to read.
Sorry.
The predicate's really hard to read.
Oh, this one. I'm sorry. This is It's just too light. Is that right? Too light. I'm so sorry. This is I should write it harder. So this is R dot SID equal to S dot SID. So basically, for every combination here, you evaluate whether the SID in R equals to the SID in S. If that's the case, you retain that. If not, then you toss it. Right? Does that make sense? Okay, so that's for the join. So of course, here our example is on equijoin, which is the most common case. Equijoin stands for equality join. But in reality, you can also have other kind of joins, like you can have equality on irrelevant columns, though I don't know why you want to do that. Or you can have range range joins, like you can specify here instead of equal, you can do greater than. I also don't want to. I also don't know why you would possibly want to do SID greater than another SID. That doesn't make sense in reality, but that's something you can do in this case, and we will show later a use case for that. And also, you can do you can do any arbitrary function. So suppose you have a user-defined function. User-defined function is basically a program you write. It can be, so for real databases, a user-defined function can be something written in SQL, in PL SQL. Also, it can be something that's loaded into SQL, say using DLL or dynamic libraries. So say this function is f, then you can do f and pass in a smaller r and s. That's a Boolean function on two tuples, one from R, one from S. If you think about this, this is basically something you define, and it can be arbitrary function. It can be even be a classifier you train using machine learning models, and somehow encode that model in a user-defined function in database. Then you can do a join like this to prove out something you don't want. So that's about the join. Yeah. So when you write a join, remember you always write the condition here as a subscript to the join operator, something like this. So only if it's an equijoin on a column that has shared the same name, say SID here, you can write SID. That's about it. So here in the slides we say when you do a natural. Sorry.
Is it r.s?
Which one?
The stuff inside f.
This one?
The
Oh, sorry. That's
no,
two
no.
arguments. Fr, comma s. Yeah. That's just two arguments in a programming sense. So yeah. So we say if your equijoin is on the same column, that's on a column that has the same name, say SID here, is also called a natural join. So for natural join, usually we will project out the second copy of that same column. So also if you have other columns that's also the same, it will also be projected out. But in your homework assignments, or in the exams, if you don't, that's also not a problem, because in reality that actually doesn't make a difference. So for natural join, you can follow the definition here. You can project out the second SID, just like this, remove this column altogether, or you can just leave it. It's all fine in your exam or homework assignment. In reality, as we will show later in real database system, this doesn't make a difference. Okay, so this is an example of natural join. Basically something we did. You join reservation and sailor, and you have a combined table which has matching SID. Okay. So this is also something we talk about of other types of join. Basically, you can write arbitrary condition, the C here. It can be arbitrary, like user-defined function, arbitrary predicates, or combination of those. Basically, a predicate logic here. Yeah, so that's for the condition join. Condition join is also sometimes called a theta join. That's because when you write some formal proof, you sometimes write theta for the condition. If you want to choose a variable for that, you typically write theta in the literature. So that's why it's also called a theta join. So that's about join. Any questions about join so far? No? Okay, that's fine. So the last one I want to talk about is called division. This is a weird operator, I would say. It's not really, so in reality, I don't think the database actually implements this. Even if there might be some optimization for that, but that's not necessarily the specific operator. So what's a division? So for a division to work, you must have two tables. This is written as, this is a bit confusing. This is A/B. Remember, this is not A/B. That's what? This is what?
Minus.
Yeah, that's minus. That's set difference. So you write a slash here. And the requirement for that is that the schema of B must be a subset of the schema of A. That's to say, suppose A for A, you have a schema of column A, column B, column C, right? Then B must be a subset of that. Say it's just a one column C here, right? This is a viable case you can apply the division operator. If your B has two columns, say C and D, and this D is different, it's not in here, right? Then this division won't apply. Does that make sense? Yeah. Okay, so suppose we go from here. What does the division say? Division say basically the result will be a tuple A prime. The A prime has a schema of sorry, I should write it this way. The schema of the result is a set difference of A and schema of A and schema of B. What's that? The result would be, the schema would be A and B. You just remove everything from B, everything in B from A, right? So basically, for if I say this is A prime, it must be something like. Sorry, I should write T prime. I write T prime here. It should be something like A and B, like two values. Okay. This is two values, not two columns. Two values, and this is to say, basically for there exists some T, so that for any there's some T in A, and for any T double prime in B, you have T equal to T prime and T prime. So this thing is something like you combine these two records together. That's to say, so for example, so if you have an AB here, say I will put some concrete values here. So suppose this T prime is 1 and 2, right? And you, for any T double prime in B, say this is 3, right? Then the resulting tuple is basically 1, 2, and 3. This is T prime and T prime combined together. And we require for any T double prime in B, you need to have this tuple in A. Then we say this tuple T prime here, say is 1, 2. It's in the result. I know this is a bit confusing, so I'll do something like I'll show you in an example. This is, if you do this with the example, it's very easy to see the result. So suppose we have several tables here, A with student number and P number. I don't know what's the P number. And you have multiple B tables which just have one column, P number. We have multiple of this. So if you do A divided by B1, what's the result? Basically, you look at all the tuples here. So the only possible values of this result is from this column, the S number column. So suppose we look at S1 here, right? So we basically combine S1 and everything in B1, and we see those tuples are all in A. So that's to say, you combine S1 and P2 here, you get a tuple S1 P2, right? And that is in the table A. Then this S1 is in the result. So for S2, you also have S2 P2 there, so S2 is also in the result. But for for S3, S4, you all have S2, the corresponding P2 in the second column. So that's why for this, the result is actually everything in S number column. That's S1, S2, S3, S4, right? And for the second example, so if you do A divided by B2, what you have to do is you look at S1 here for everything in the S number column, every distinct one. You look at S1 and you combine that with everything in B2. So you get S1 P2 and S1 P4, right? And you look at that, you find there are those tuples in the first table in A. So that's to say, say S1 P2 is in A, and S1 P4 is also in A. That gives you S1 is in A divided by B2. That's what we are saying here. But for example, suppose for S3 here, what you are looking at is every combination of S3 and everything in B. That's S3 P2 and S3 P4, right? And you try to find are these tuples in A. This one is in A, but this one is not, right? So that gives you S3 is not in A divided by B2. So basically, you require a value in the S number column with any combination in B2. You must find all the combinations in A so that this particular S number will appear in the result. So because of that, you only have S1 and S4 in the result, right? Because for S2, you don't have S2 P4 in A, and for S3, as we said, you don't have S3 P4 in A. So far so good.
Yeah. So why, when you have P2 in the first example there,
Yeah.
you have P2 in both examples, and why doesn't it pull out all of the S1 through 4?
You mean for which example? A divided by B1 or B2?
If you have P2 in both of them, it should do the same thing in both of them, right?
No, actually it's a little bit different. So for here, remember the division is actually require you to have every possible combination in the original table. What does that mean? Basically, as I explained, for S3, you combine that with everything in B2, and your end result is two tuples, right? Two records. That's S3 P2 and S3 P4. You require those to appear in this relation, in A relation, at the same time. So they must have everything there, so that S3 will appear in the end result. That's what this division says. That's not to say if you have a result here, say you have S3 and P2 here, then S3 will appear in the end result. It's not any, it's all. You require all of them to appear in the original relation. remember that it's a little bit different. So does that make sense to you?
Yeah. So what is SNO and why is it different than PNO? What is one the key? Is that why we're combining it with the other table?
Yeah, it's actually not relevant for the purpose of this operator. We will show a concrete example that will make more sense to you. But just for the semantics of this operator, it basically requires, if you want something in the end result, you want to have everything, every possible combination in A. That's what you're saying. So you can think of S number as some kind of key, and P number as some kind of attribute you want to talk about a student. Then you require this student to have every possible P numbers in the A table, and you want to find out all those students.
So what if A had 3 columns?
What if it has 3 columns? Yeah, good question. So if A has 3 columns, basically you are looking at, say, I'll draw an example here. Say A has S number, say a name, and a P number, right? So this is A. I'll use a new symbol, A prime, right? And I'll use B table, which still only have this P number here, right? So basically, you are looking at all the combination of S number and name, all the distinct combinations, all right? So 1 Smith will be one of them, and 2 Smith will also one of them, right? This is the every say this is the every combination of S number and name, right, in the A table. And what you are trying to do is that, say this B here contains 2 tuples. Say its value is 1 and 2, okay? All right? Then what you are trying to do is you check whether 1 Smith, 1 is in A, and 1 Smith 2 is in A. So basically, you are trying to check this condition. If this is satisfied, then 1 Smith will be in the result of A prime divided by B. Does that make sense? And for this, you do the same. If everything is there, then it's in the end result. If not, then it's not. So yeah, I know this is the most complex operator, I would say, and it's a little bit confusing at the first glance. But yeah. Do you have questions about this? Or is it still confusing to you? Yeah, we'll show an example. Maybe that's going to be clearer with more semantics that makes more sense. We'll come back to this. Just show you the example. Maybe that makes more sense. Right. This is a perfect example. So suppose we want to do for our original sailor boat and reservation example. So suppose we want to find the names of sailors who've reserved boats. So basically, we want to find those those sailors have reserved everything. That probably means this guy is capable of driving everything and he's a good sailor. Maybe we want to find those people. So what do we do? Here, this actually can just be expressed with using a division operator. Why is that? Because so basically it matches the definition of division. So what you want to do is that for every distinct sailor there, you want to find their names. And what's the condition for the sailor? That's basically he has reserved everything, in your boat inventory. So if you think about your boat table, you have SID, BID, and day there, right? So day is irrelevant, but if a sailor has every possible combination with the boat ID, then it will appear in the result, right? That's what we are trying to do. We want to find the sailors who reserve everything in your inventory. So that's where we might use this division operator. So, but for that to work, remember our reservation, we have 3 columns. We have SID, BID, and day, right? So basically, a sailor can reserve a boat on different days. That's also possible, right? But for the purpose of this, we don't actually care about the day, right? So what do? We can just project out that thing. So we don't care about the day, so we project out that column so that it will only contain the list of sailor ID and boat ID who have ever made this reservation. So the end result will be all possible reservation records that sailor has reserved a boat, right? So suppose you have, for example, suppose you have sailor 1 reserved a boat 2 on day December 11th, and he also made a reservation on December 12th. And you know there's another sailor who made a reservation of boat 1 on December 13th, right? And you also know the sailor 1 has also made a reservation on the boat on another day, December, say, 12th. Maybe this guy reserved 2 boats at the same day. So the results, the projection will produce a table where you only have the SID and BID. That's everything distinct in the first 2 columns, right? So that you will end up with 1, 2. That's to say sailor 1 has ever reserved boat 2, right? And also you have sailor 2 has ever reserved 1, and sailor 1 also have reserved 1, at least once. That's what you end up with. This is the result of this, right? So what you are trying to do, you want to try to find everything here. Like you want to find all the sailors who have reserved all the boats. Suppose every boat has been reserved at least once. So basically, if you have a boat, it's in your reservation record. So what you are trying to do, you want to try to find all the sailors who have every possible combination with the boat IDs, right? So for here, you have 2 boats. You have 1 and 2 boats, right? You have 2 boats. And what you are trying to do, you want to try to find all the sailors who have ever reserved both boats on some day, maybe not on the same day, but the sailor had. So what you do a division here. So this is the table for sailor and BID, right? This contains all the possible reservation records. And you divide that by what? By the boat, right? And where's your boat? Oh, sorry. I should write R here. And where's all your boats? Your boats is in the B table, the boat table, right? And this will give you all the possible boat IDs in your inventory. So if you do a division here, what you try to do, suppose this gives you 1 and 2. So it's the same situation here. You look at sailor 1. This is sailor 1, right? You try to find whether 1 is in this table. And you also want to try to find 1, 2, is it in this table as well? So do they exist in the result? Yes, because it's here and here, right? So that means sailor 1 has reserved all the boats in your inventory. So he should be in your end result, right? So 1 is the in the result. I'll write it here. So basically, you end up with SID 1, that's in your result. And then we look at Sailor 2. Sailor 2, right? Okay, so for Sailor 2, there's 2, 1 in that, right? 2, 1 is here, right? So it's here. But 2, 2, is 2, 2 there? No, right? 2, 2 is not there. So Sailor 2 won't appear in your end result because he has some old, he has never reserved. Yeah. So this is a possible case where you might want to debate. Basically, you try to find somebody who has done everything, like who has a record, every possible record in the original table. So does that make sense? Yeah.
Just let me make sure I understand this correctly. So if, for example, you had not projected out
Right.
the date in the initial relation, does that mean that all the tuples of Sailor and date were on that date if gotten all the dates?
Yeah, it will be a different query because you have a sailor on different day. If he like that will be so for each of your day, if this sailor reserved all the boats on a day, then he will be in your result, right? Otherwise, because here you want to find all the names of sailors who's ever reserved all the boats, not necessarily on the same day. So that's why you want to project out day. But if you want to find someone who's like really rich, he's gonna reserve everything in your inventory on the same day and have a sailing computation, right? Then that's your query. You don't project out those things. Yeah. So yeah, but this is actually a little bit more complex because you also need to find the names. That's where you need to do a join, right? Since you already have the SID here, so your end result will be the SID of all the sailors who's reserved all the boats, right? So you also need to find his name, but where's that name? It's in the sailors table. Yeah, in the sailor table, right? You're right. So that's why you want to do a join here. Basically, you join them based on the common attribute. If it's a natural join and they have the same name, you do not have actually specified that. You can also write SID as a subscript to the join operator. If not, it's implicitly all the all the columns with the same name. So basically, you are joining your SID here with the same SIDs in the sailors table. And finally, because you only want the names of them, so you do a pi, you do a projection there to project out all the names, right? So this will give you all the names of all the sailors who reserved all the boats. Yeah. So any questions about this so far?
Are those two commands separate?
Oh, yes, because remember that row is a renaming operator, right? So when you do this, actually you can inline this. So basically you are renaming the result of this, right, to something called a temp SIDs. You can write it in two separate relational algebra. Also, or you can just plug in everything in your second part of this row operator to this text SIDs as a single relational algebra query. So basically, you will write pi name, and temp SID is basically just replaced by that part, pi SID BID R divided by pi BID B. And you join that with the sailors table. I'll just write S. Right? You can also write that. It's just sometimes it's easier to break things down into multiple components so that you don't get confused. Right? So yeah, that's about the. Yeah, I see. Well, guys, a lot of you are confusing. Yeah.
So is the result of a row operation a column?
Sorry.
Is the result of a row operation a column?
No, actually, basically row is something like a side effect. You just
there's no output.
yeah, there's no output for row. There's output for the second part of the row. So you just give the names of them.
I was just wondering, like, can I put that inside?
Yeah, you can put like if you put that into, as I said, if you put that into this, you don't put a row there. Row is basically side effect. It's just for convenience. If you want to like, one thing is if you want to break something long down to very small pieces so that it can be easier to reason about. Also, something else you can do is that you might want to use your intermediate result multiple times. If that's the case, you can also use a row, right? So that's where the row. The row is basically a side effect. Yes.
The symbol P was for renaming or for joining?
Yeah, it's not a symbol for P. It's a Greek letter row. If you are using LaTeX, it's this thing here. Oh, sorry. This letter.
So it's for joining or for renaming?
Row is for the whole query. So basically, it's for the second component of this. The row basically does. So do you see the division there, right? It basically renames the result of the division to a temp SID. Yeah. So basically, temp SID refers to the result of that division. Yeah.
Is it like an assign?
Right.
Is it like an assign?
Assign? You mean like assign in programming language? Yeah, something like that. But yeah, you can think of this as if you do C++ programming, you have reference, right? This is something like a reference. Basically, it refers to one.
So it's leaving the row.
Yeah, changing.
I'm going to leave the column.
Oh, you can also change the column names. Like I said, you can do row.
Like that example.
Oh no. Here, basically, if you don't specify anything, then the column names are
What names are changing?
What names are changing? Oh, nothing. Actually, the column names are not changing here. The only thing you do is that you refer this intermediate result as a temp table. So this, you can think of this as a temporary table, and it has a name now. It's called temp SID. Yeah, just change the name of the table, but it's not really a base relation. It's just a temporary result. Yeah. So yeah, maybe if you have more questions, there will be an office hour just at 2, so you can just come up or talk to me. Come talk to me later. If this is still confusing to you, I know this is a very hard operator to think about, and that's why maybe I don't know any database that actually specifically implement this division operator. Yeah.
So if you go back a slide or two, you have you're describing the division operator, but how does it help? There's a big long mathematical statement that you skipped over.
Which one?
I don't see anything.
Oh, I'm sorry. I'm so sorry. I should yeah. It's here. This
Yeah,
one?
that one.
Yeah.
What is
So,
that?
what is that? Do you know what these two operators are? This is for any. This is exists. Basically, this is just pure mathematical way to say this.
So
So,
that's the same as whatever you were writing on the board?
right, it's the same as I write on the board. Just this is a more concise way to write it. Just think about that. This is just say the results would be an x, which has the same schema as if you minus b subtract b schema from a. This is the x schema, and for every y in B, you have a combination x, y, in A.
And X and Y are rows?
Yes, X
Or are they
is a
columns?
row in the end result, Y is a row in B. And this is basically you concatenate these two rows together so that they have the original schema of A. And you want for anything that's in B, you want to find every possible combination of anything you find in the end result in A. That's basically what this mathematical term is saying. But if you think about the later example of a boat and reservation, maybe it makes more sense in an intuitive way. Yeah. Sorry. If this is still confusing to you, maybe we should talk later. Maybe we should put it up.
Is field a row or column?
Is field a row or column? What do you mean? Oh, two fields? Fields are the columns.
Oh, you said rows earlier.
Right.
Okay.
Yeah, so if you have any questions, we can talk offline about this, about division. So, yeah, here are the examples. Skip. Yeah, and as I said, all the compound operators can be expressed in basic operators, so this is the way you do this. That's why we have this operator for this purpose, because as you see, this is fairly complex to write as in terms of the basic operators. So that's why you might want to have that. Maybe I should explain this a little bit because, yeah, I should explain this a little bit. Just using the remaining time, 5 minutes, that's all I have left. So still the same example, suppose you have two columns, SID, EID, and you have 1, 1, 1, 2, and 2 columns. And you want to find every SID that has every possible combination with BID in this table. So that's to say you want to find this is A and your B table, sorry, S table, and B table would be BID, you have 1 and 2. So S divided by B should be just one column and one row. It's work, right? So if you want to express that in the basic operators, what you do is basically you first look at all the possible things, all the distinct values in the result relation. So that's basically chi SID of the S table. That's everything that's in all the columns in S but not in B. You do this projection. This gives you all the possible results in this division. Then what you do, you want to find every possible combination of that. That's basically cross product with B. So this gives you all the possible combinations. So it will be like this: SID, EID, and you have 1, 1, 1, 2, 2, 1, and 2, 2, right? This is all the possible combination of SID and PID, right? And you want to find if something that has all the combinations, right? If you negate that statement, it's basically saying you want to find something that doesn't have an entry. It's missing some entry there in the original table. Basically, you are trying to find you can try to find something that have all the possible entries there, like all the sailors with all the possible PIDs, right? But you can also try to find something that's missing some PIDs, like 2 here, right? What you do, you basically subtract this from all the possible combinations. What you get, you basically find this SID, BID, and you get a reservation record for 2 and 2. That's something what's missing from the table, the possible combinations, right? In one of the possible combinations, this is missing from the original table. And that's something you don't want in the end result, right? This is something you don't want in the end result. So basically, you try to find out what those SIDs are. So you do a projection. So this gives you all the SIDs that's missing some reservation record in your original result. And this is something you don't want. So you basically subtract this from your all possible answers. Right? So let's just say you have 1, 2 here. And I know there's this particular two here is missing some reservation record in the original table. This guy didn't reserve the boat 2, right? So this shouldn't be in the end result. So you subtract this from that, which gives you all the sailors who have reserved all the boats, right? So this is how you express this A divided by B using the basic operators, just pi and cross product and set difference. So it's maybe this way. I don't know if there are like I said this in 3 different ways. Just a set, formal mathematical definition, and also in terms of the basic operators and a concrete example. So I hope this won't be like too confusing to you, but if you do, please come to my office later, maybe during office hour or whatever TA's office hour. I think we'll end there here. See you next time.
No.
Yeah.